We tried really hard to cover a lot yesterday under trying conditions. It was hard at the end of the day and all that kind of thing. But we did get there. We took this idea of volumes, right? And we established at least the basic result. That if we were to take a function, right? Instead of working out area with an integral, we can work out volume by. Now, what was the formula, the result that we ended up with? Do you remember?
Pi.
The first thing is pi.
Right. Dx.
Okay. Then the integral. You slap in whatever boundaries you like. And then what you are actually integrating is y squared dx. Okay. So you remember together, this pi really belongs with that y squared. So it's just like pi r squared. Because these volumes are not just any, they're solids of revolution. So we're adding up a whole series of circles together. Okay. So I think we arrived there, and then we were exhausted. We didn't really get much opportunity to do examples apart from like spheres and all the results you already know. Okay. So let's have a look at something we don't know and see if we can work out how does this volume actually get calculated. So here's a function. Let's pick some boundaries. I'm going to go from 0 to 3. Okay. So there's my 0 there. So I'm going to erase this part. Don't you love that sound? One of the advantages of whiteboards over chalkboards, because the comparable sound from chalkboard is terrible. And then up to 3, so I don't know, put it wherever you like. Put it there. Okay, now we're used to talking about the area. If we were trying to work out this area, we'd say it would be the area under x squared plus 1 bounded by, now what are the other 3 boundaries? There are 3 other boundaries at play.
The x-axis and the y-axis.
Number 1,
X equals
the x-axis. You could call this the y-axis, but a better way to say it, even though it seems the same,
0.
is x equals 0 and x equals 3. Because it's not always an axis. It could be x equals 1 and x equals 3. Or whatever. Okay. Now therefore, sort of, if I draw those boundaries in, another way you'll hear this volume that I'm about to draw, right? They will often refer to it as this area being rotated around. Okay? So they'll say the area under x squared plus 1, bounded by blah, 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 is rotated around the x-axis. And often on the diagram, they'll provide you, the direction it's going. Okay, so, are you ready? I'll just wait until you're all good to go. Cool. What's this volume going to look like when we actually do the revolution? Well, it is very similar to the cone that we had before, but it's kind of chopped off. But unlike a cone, the slant plane is not a straight line, it's curved. Okay, so we've got to take that into account. So one way to think about it is just take the beginning and draw the circle that comes from that. So it might look something like this. Remember, we're looking at a side on, yeah? So there's one circle that comes from this. There's a circle that comes from this, which obviously is much larger. So, by the way, be careful. It's probably worth getting out your ruler and measuring that distance so that you've got, do I here? No, I don't. So that you get the symmetry, so your shape looks kind of decent, okay? So that looks to me like, that's one hand span for me. So I'm going to come down around there, okay? So here is, which way should I do it? I probably should have done that dotted. Here's the other circle. Okay, so if you like, I'm looking at it from this angle. Okay, so that's why I can see this, if you like, is the top, right? And this is the bottom, so that's why I can't see this part. And how do you get the rest of it? Well, it's going to be this curve, and you flip it upside down to connect with us. Okay, now the next part is not necessary really, but it just helps with visualizing things. I'm going to put a few lines in here, things like this. Just to make the curvature of it a little more obvious. Visualizing is so important. It really, really is valuable. Okay. So there's the volume. Now how do we calculate it? Every time, no exceptions, I do a volume question, I always write the formula with no things put into it. No boundaries, no functions, anything like that. Because, do you remember I told you yesterday, when doing volume questions, there are 2 common errors that people make. And neither of them are the actual integration. You get quite good at integration, right? The algebraic process. Usually you forget the pi, or you forget the squared. okay, because you're focusing too much on other stuff. So writing down the formula is the best way to guarantee you're going to get all the pieces in. Because if you write the formula wrong, like if you write that, it doesn't even look right, okay? So you're like, oh, something looks like it's missing. And in the same way, if you forget the squared, you're like, that's an area, obviously, right? So that's why I write down the formula first. Okay? And having done that, now I'm going to substitute some actual values in. Okay, so the pi is out the front. What are my boundaries? It's it's 0 to 3 because I'm going around the x-axis, so I'm interested in these x boundaries, right? So 0 to 3. Now y squared in this case is that squared because that's y, yeah, with respect to x. Okay. So this is not too problematic. Let's expand this guy, and then we can just treat it as a polynomial and raise the powers, divide by that. This is x to the 4, 2x squared, and 1. Okay, and then from this point, there's nothing unusual about it. You could treat this just like any other definite integral that you have to work out. Okay, so this is pi from this. What's that going to be? 2/3. Plus x from 0 to 3. Yep. What do we got? What's 3 to the power of 5? 3 cubed is 27. 3 to the 4 is 81. So the next one up is 243. On 5, that's going to be 3 cubed. 3 cubed, so 2/3 times 27 plus 3, and then I'm going to subtract. All of these will be 0 for the lower bound. Yeah. Okay, what's that? I'll do a bit of simplifying before I get my calculator out. 2/3 of 27 is 18 plus 3, that's 21. Okay, now that's a fraction I can't really be bothered. What does it come out to? Has anyone got their calculator there? $102? Exactly? Like as in no fractions or anything? Really? Huh? That's a 5. That's a 5, buddy. Let's try that again. I was like, this doesn't see. Something smells from me.
348 on 5.
348 pi on 5.
I can't calculate anything.
Okay. Calculation was fine. It was the reading that was. Sorry, I guess my writing. Okay. So this is the integral that I worked out. I think the best way to conclude, rather than just slapping units on there, is to have a second line, or put off on the side here. Volume is, and this is, I don't have any units, so it's just units, okay? And it's cubed, because it's a volume. Great. Now that's not too difficult. But yesterday I started talking about the fact that there's more than one kind of volume, right? So. Hi, good to see you. So taking the same function, right, and even taking the same boundaries. So I'm going to have this kind of shape here, and I've got 0, and I've got, that'd be 3. Okay. There's another volume that I can make just as easily out of this, okay? Because here I rotated around the x-axis, right? But surely I can rotate around the other axis, right? I can rotate around any axis I like, right? Now, before we start doing the maths of it, what's the shape going to look like? How would you describe the shape?
Football field. It's like a bowl with
okay, so you can think of it a couple of different ways. It's kind of like a bowl with a pointy end on the bottom, so it's not going to sit very well. It's kind of like half a football if you cut it in half, because it kind of does come to a sharp point. The important thing is you get the symmetry, right? So here, if I draw the other side of it.
Wait, does it come to a sharp point?
Oh, sorry, no, it's a parabola, so it's actually it'll have a stationary point, yeah. So it's going to come up to there, and then because I'm going around this way now, so if you like, put on your diagram that kind of arrow, right, showing the direction. The circles I'm going to form, which I'm going to add up, oops, they all look like that. So there's our ball, if you like. Though it's not that ballish, it's not very useful as a ball because it's solid, so you can't put anything in it, because they are solids of revolution. We'll get to hollow stuff later, okay? But this is the shape. You can make it look more round if you like. There you go.
Wait, I'm confused.
Okay.
Why isn't that bit rotating?
Which part?
Like the one under the curve.
This part.
Yeah.
Yeah, okay, now, we can work out what that is, but I'm going to leave that for now because it's going to be a different kind of shape. Okay? So, Swazi's picked up a useful thing, right? Here, I took the area underneath and then I rotated this way, right? Here, I've taken the area above and then I'm rotating. Now, you tell
X
me,
to the Y, right?
I'm actually going to suggest that this is a more natural way of taking this volume. Why would it be more natural to take, what actual area results? Instead of this area here, it's going to be, I'm taking this area.
It's like the area inside the parabola instead of underneath it.
That's right. Now, because I'm rotating around the y-axis, right? Think about this with me. Remember the dx was like that little width there, every little width that I've got, okay? I'm not going to have widths here, right? Because the circles that I'm getting, they're stacked up on top of each other like this, vertically, right? So they're not going to be dx wide. Instead, they're going to be dy
Long.
high or long, if you like, okay, whichever way you think about it. So this volume, I'm going to calculate it differently. It's still going to have the pi out the front. The pi comes from the circles that I'm getting, right? But I'm not going to write a to b. I'm not going to write a to b, even though it's you know, in some ways it's just letters, right? And you know, call them whatever you like. I'm going to call them c and d just so I distinguish them from a and b are always the x boundaries, right? 0 and 3. Okay. But I'm now thinking about a different axis. Okay, I'm thinking about rotating in a different way. So I'm thinking about different boundaries. Now, in this case, what are the boundaries? Good. Which you simply get just from substituting these in to the actual function. Yeah. So there's 10 up there. Now, before we had y squared dx, okay? Because y squared was like the radius squared, and dx was the width. Well, now the radius is not y squared; it comes from this horizontal thing, and horizontal is x, right? So it's x squared dy. Okay, you see how that's different? It's just a swap. Okay, the way I tend to read it, right? Just like we'd say, oh, this is integration with respect to y, right? I also think of it as rotation with respect to y. Okay, it's a different kind of rotation. Okay, now, just like with this question, I'm just going to write that formula down, and now I'm going to put some actual values into it. Okay, now, I think Jesse already told me the actual boundaries I'm interested in are 1 to 10. Okay. Now, this is kind of nice for us. In this case, x squared actually already appears in the equation we started with, right? All I have to do is rearrange a little bit, right? So x squared on its own, y minus 1. Yeah? So that's what I'm going to integrate. And now I've just turned it into a definite integral, and off I go. Okay? So let's go ahead and work out what the values are. Pi. What is the integral of y minus 1?
What, sorry? Oh, y squared minus 1. Y squared.
I don't have to look at you for you to answer. Y squared on 2 minus y. Okay? 1 to 10. Okay? So from here, it's pretty standard, yeah? Pi outside of. Now save you some time. If I remember this properly, I think it's that. But you can go ahead and verify it.